Welcome back, everyone. So, we are going to continue our discussion on seismic response of multi-degree of freedom system, and we are going to look into few examples today and see how we can apply the response spectrum method to a simple shear type building, and then using that, how can I find out the peak responses for the displacement at different stories, as well as the story drifts and the peak values of the base moment using a response spectra. Okay. What I'm going to demonstrate the response spectrum procedure on a 3-story building. Okay. But remember, the same procedure can be extended for any other type of multi-degree of freedom system. Doesn't have to be a shared type building or anything like that. Okay. But here, because it's easy to draw and everything, I'm just going to demonstrate that example using a multi-story building. Okay. So what we are going to do is basically modal analysis procedure. Okay. So modal analysis procedure is basically when we consider this decomposition into several single degrees of freedom system. And the response spectrum procedure is when we consider peak responses. Okay. So modal analysis procedure can be, it's a general procedure to basically find out the response of at any point of time. Okay. Response spectrum procedure is a special case when we are talking about only the peak responses. Okay. So just keep that in mind. So what I basically have here is let us consider a 3-story building. Okay. And this 3-story building has masses at each level M1, M2 and M3. Okay, and the story stiffness is as K1, K2 and K3. Now, there is a ground motion now. Okay, let us say ground motion, ground excitation UGT, because of which okay, I have these displacements here, which are U1, U1, U2 and U3. Okay, so we can consider basically equilibrium at each floor. Okay, I'm not going to repeat that, but if you like, you can just draw the free body diagram of each floor, or let me just do that anyway. So I have here M3, okay, U3 plus UG, total acceleration of mass. Okay, and then because of the floor below, I have K3, U3 minus U2. Okay, for the second floor, I have equal and opposite force on this. So K3, U3 minus U2, pseudo force M2, U2 minus, no, not U2, U2 plus UG opposite to the direction of motion, and then K2, U2 minus U1. Similarly, for the first floor, okay, I have M1, U1 plus UG, and then equal and opposite force here, K, U2 minus U1, and then K1, U1 here. So you can write down the equation of motion. Basically, we'll have the 3 equation of motion. Okay, M1, U1 plus UG plus K1, U1 minus K2, U2 minus U1 equal to 0. Similarly, M2, U2 plus UG plus K2, U2 minus U1 minus K3, U3 minus U2 is equal to 0. And then the third floor, which is basically M3, U3 acceleration, U3 plus ground acceleration, then K3, U3 minus U2 is equal to 0. So I can also write it in terms of matrix form M1, 0, 0, 0, M2, 0, 0, 0, M3. u1, u2, u3. So by now you should be very proficient at least with setting up this equation of motion. Okay. Building should be very easy for you, especially the shear type building. It would always be of this form if the degrees of freedom are defined at each level. Okay. So this is my stiffness matrix u1, u2, u3, and if I bring all these m1, u1, m2, u2 to the right hand side, what do I get? Basically m1, m2, m3 times ugt. Now I would like you to recall from the last class the things that we did. Okay, so what did we say? We said that this can be further written as mass times acceleration vector plus stiffness times displacement vector, and this can be written as mass times the influence vector times ugt. Okay, and like you might have questioned that why we are using influence vector at all. Well, it is easier when we do multi-story building that it is simply in terms of this, like vector 1, the influence vector is 1 1 1 here, but you will see in many other type of multiple degree of freedom system your influence vector is not 1 1 1, it would be something different, and in those cases writing down the influence vector basically provides you a generalized equation of motion. You don't have to worry about whether it is a shear type building or whether it is other type of multiple degree of freedom system. Okay, so for the general case, okay, the equation of motion is m u acceleration vector plus k u and then minus mass matrix times influence vector times ugt. Okay, now we discussed how to get the influence vector for different type of systems. Okay, let us now see if we have the damping in the system. Okay, all I need to do, okay, for the damping cases, okay, just write down this equation of this form: additional damping matrix here times the velocity vector, okay, plus k times u vector. But you need to be careful. Usually damping matrices are not given, and many times it need to be constructed from what? Do you remember? It need to be constructed using damping ratios, right? Zeta 1, zeta 2, like that. Okay. And in those cases, my C1 or Cn becomes, okay, what is my Cn? It is 2, or if I write it like this, zeta n is Cn by 2 m n omega n. So Cn becomes 2 zeta n mn omega n. Okay, so this would be given to you zeta n. Okay, and you need to formulate that from the and we saw that what were the different methods? There were mass proportional matrix, damping proportional matrix, and there were also Rayleigh damping. Okay, in which case we formulated as linear combination of mass and stiffness matrices. Okay, so in those cases, basically, if the damping for one or two modes are given, we can find out damping for the other modes as well. Okay, if that is clear, let us write down the single degree of freedom equation for the corresponding this equation. Okay, so if you remember, we can write it down as dissociate single degree of freedom system, or for the nth mode, we can write down this equation of motion as mn times qn plus cn times qn times kn qn is equal to, let us say, this quantity would here becomes, or P effective or Pn, let us call it Pn effective T. Okay, where Pn effective T is nothing but for the nth mode. Okay, or I'll just delete the subscript. That is just called directly Pn. Pn is nothing but phi n t times the vector. So this is, in this case, would be phi n t times mass times L times UGT. Okay. So this is what we get for the seismic excitation. Okay. And this is our N uncoupled single degree of freedom system. Okay. These are all uncoupled. Okay. And solution to these type of equations we already know. Okay. Can write this as 2 zeta n omega n qn. So I'm dividing it with mn. This would become omega n square. Okay, and this would be basically Pnt by Mn. Okay, where Pnt by Mn is nothing but minus, no, not, we'll have to write down the phi t here. This is phi t times m times the influence vector and UGT, and this divided by Mn. And if you remember, okay, this is what? This is gamma n. Okay, this expression here is gamma n, which is also called modal participation vector. Modal participation vector. Okay. So the equation that we need to solve is basically, let me just zoom it out. The equation that we need to solve basically becomes this. Okay. Qnt plus 2 zeta n qn, not qn, omega n qnt plus omega n square qn, and this is equal to zeta n UGT. Now, except the term here, I have the solution available for the rest of the equation. Okay, and let us say the solution that we have available for is this equation here. Okay, because this comes from the, this is basically somewhat, you can think it like, relationship between the single degree of freedom system and the multiple degree of freedom system, right? Apart from that, if you just consider Q to be any variable, okay, this is a single degree of freedom system. Okay, only this zeta n, the modal participation factor, is what represents how my single degree of freedom system is related to the overall multi-degree of freedom system. Okay, so we already have solution for this available from the standard equations or charts or whatever, if it's not a ground motion. Okay, so we have, and this is the equation that we use when we try to find out response of a single degree of freedom system of a single degree of freedom system subject to ground motion. Okay, UGT. All right. So if we want, and if we are only considering linear system, then we can say that if we know the solution for this, the solution for this equation would be simply excitation, whatever the solution we get for this, multiplied with this factor, because it's a linear system. So basically, if we know the solution for this equation, solution for this equation would be simply gamma n times dnt. Okay. All right. And so this was the solution in terms of time. If you wanted the maximum peak solution as well, at least for this single degree of freedom system, it would again be related by the same expression. Instead of dn, it would become dm max. Because remember, only dn is varying in time and qn is varying in time. Okay, gamma n is just a function of the mode shapes and all those things. Okay, this expression here, there is no time here. Okay, so whenever dn reaches the maximum value, qn is basically that multiplication multiplied by this factor here. So it would reach the maximum. So at least for that single degree of freedom system, if I know the dn max, qn max is also known. Okay, all right. Now let us see, we also talked about how to do the modal expansion of the excitation vector, remember? And we said that if my applied force modal, let us say expansion of excitation vector. Okay, so we said that if somehow for some special cases my p vector, the applied force vector, can be written as a spatial distribution S times the same time distribution, and this is specifically true for seismic excitation, then I can perhaps find out what is the contribution or what is the basically expansion of this vector S in each mode. And we said that the modal expansion of vector S represented how much is the inertial force in each mode due to applied excitation. Okay, so we said that we can write down the expansion of this as, let us say, n number of vectors. So I'll call it n here, and I have already derived the expression for these in the last class. Phi n, where this gamma n is nothing but phi n to the power t times s times the mn. Okay, and if you consider seismic force, what is the P effective? P effective is mass times L times UG double dot T. So if you compare, this becomes your S. Okay, the spatial variation. This is your time variation. So basically we can expand it. And we also saw that if that is the case, okay, then how can we actually expand the same vector, basically ML. Okay, so if I substitute S equal to ML, it can be expanded using the same expression n equal to 1n. So all I need to do is to find out zeta n here and substitute S equal to m times the influence vector to get the modal participation vector. And once we get that, it is very easy to actually expand the excitation vector in terms of inertial forces in each. Okay, and we also said that if you want to find out the internal forces or the element forces, okay, there are two procedures that you can utilize. The first procedure is finding out UNT, which is the contribution of nth mode to the total displacement response, as K times, sorry, not UNT here. Let me write here as okay, directly utilizing this expression here. Okay, so if you have UNT available after you have found out your QNT, then, and if you have, let us say, multi-story building, you can find out, let us say in the nth mode, the story shear in the jth mode would be story shear Kj times Ujn and Uj minus 1n, okay, as the drift. Okay, this is the first procedure. Find out the UNT and then find out the story shear individually and all the forces. The second procedure was equivalent static procedure, in which, okay, we find out equivalent static forces as stiffness times the displacement. Remember, this is for the nth mode. So K times Un is equal to phi n, okay, times Qnt here, okay, and K phi n is nothing but omega n square mass times phi n times Qnt. Now either you can leave it at this point or you can further simplify it, okay, by utilizing this expression that we had derived here. So what you can do in this case, let us write down, remember your phi n is nothing but, if you look at this expression here, okay, I can write down the total response as where is Sn? Yeah, Sn here as phi n m times this expression. Okay, now Qnt is basically what here? If you look at Qnt is nothing but always the modal participation factor gamma n times the dt that you obtain, where dt is the response of the single degree of freedom system without any factor gamma n, and dt, let us call dnt. It is also related to acceleration in the same mode. These are pseudo acceleration, okay, utilizing this relationship. Okay, so what we can do here, we can write down gamma n and omega n square, and dnt is basically an. So this would become ant. Now what is this expression here? If you look at this expression here, this is nothing but Sn ant. So if you have found out the dissociation of mass times L vector, which is basically S, okay, all you need to do in each mode, just multiply with the modal acceleration ant, and that will give you the equivalent static forces. Okay, and if you want to find out unt, that's not difficult as well. Okay, unt you can directly find out as gamma n divided by omega n square times phi n and ant. Okay, so what we are going to do, actually we are going to do an example today, okay, and then see how we actually solve this system and find out the basically the displacement response as well as the internal forces. Okay, and we'll also see the response spectrum analysis. So response spectrum analysis, as we already discussed, let me just again summarize that as well. So in response spectrum analysis, so till now whatever we have done, combining the response at each time instance. Okay, but that is not easy. Many times I don't want to find out, the time variation of the response. And let us say the peak response is given to me something like this, ant as a function of, or not ant, let us just call acceleration here. It might be given in SA by G or A by G, whatever notations you're using, and this is the time period. So response spectra is always defined for a single degree of freedom system. Now my different modes will have different time periods. Okay, and they will have different peak responses depending upon the time periods of each mode. Okay, I hope that is clear. So I have now a multi-degree of freedom system. Okay, in multi-degree of freedom system, I have decomposed into n single degree of freedom system with different time periods. Okay, and if response spectra is given, I can say that each mode will have different peak response depending upon the time period. Let us say T1, T2, T, and so on. Okay, but they will also occur at different time. Okay, so, and if an is given, or displacement is given, doesn't matter. Always remember this expression an equal to omega n square times dn. Okay, this is a good approximation if damping is smaller than 20%. Okay, then this is a good approximation. I mean, this is not the approximation. Approximation is this, that this is the UT max, maximum. Okay, this is a good approximation. So you can directly utilize these expressions. No need to worry about whether this is exact or not. Okay, now let us look at what is the problem statement here. Okay, so basically, what do we know? We know maximum value of UNT, okay, as UN max for n equal to 1, 2, 3. Okay, this I know how, because response spectra for that particular ground motion is given to me. Okay. Now, what we need actually, we need maximum of UT, which is the total response. Okay. So basically I need this maximum of summation of all such UNT here. Okay. This is what I need. And as I said in the last class, this might not be equal to summation of maximum or UN max of individual mode, because maximum response might occur at different point of time. Okay, so then what do we do? Well, remember we showed this graph. Okay, if I consider different modes here, these are single degree of freedom system. Okay, let us say D1, this is D1. Remember, how is your U and D is related? If you remember, sorry, Q and D, your Q is nothing but this times Dn. Okay, so just remember that. Similarly, your An is omega n square Dn. Okay, and Dn, it becomes, if you want to write down Qn in terms of An, then you can further write it as omega n square times An here, if the An value is directly given. Okay, so I know that my D1 max occurs at this time. This is my D1 max. Okay, D2 max occur at this time. Let us call this D2 max. And let us say D3 max, although looks like at the same point, occurs at this point. So the idea is, I know the maximum response of each three mode, and all such n modes, how do we combine them so that we get approximately the D max and subsequently the U max. Okay, so as we said, there are different methods. The method that we would be utilizing is called SRSS method. Okay, square root of sum of squares. Okay, which basically say that D, the maximum would be D1 max square plus D2 max square and so on. Okay, and there are other type of combination as well, but we are not bothered about that. Okay, so let us do an example. So basically, the same three-story building that we have, I'm now giving you the value of M1, M2, M3 and K1, K2, K3. Okay, 25, 10 to the power 3 kg. This is 250 into 10 to the power 3 kg. And this is 350 into 10 to the power 3 kg. So these are the story masses. Okay, story stiffnesses are 3000 kilonewton per meter. Sorry, not 3000, 30,000. 30,000 kilonewton per meter. Then this is 20,000 kilonewton per meter. And then this is 10,000 kilonewton per meter. Okay. All right. Now the first step is for you to do here. Give 1, omega 2, omega 3, phi 1, phi 2, and phi 3. Okay. Remember the mass matrix is 350, 0, 0. What I'm going to do, because we have to go to the next step as well. I'm going to give you the frequencies and the mode shapes now. Just assume that you have come up to this step by doing it, and then we will further proceed. Okay. So let me just write down frequencies that you will get is 4.52, 9.63, 14.38. Okay, and similarly the mode shape I'm going to write it here. I'm normalizing with respect to third story. Okay, so this is 0.3 here, 0.64 and 1.0, and this is phi 2 as minus 0.7, minus 0.62, and again 1.0, and this one phi 3 is 2.34 minus 2.62, then 1.0. Okay, so once you get the mode frequencies and the mode shape, remember you have got your single degree of freedom system. The next step is to how to relate the response of a single degree of freedom system to multi-degree of freedom system. And how do we do that? Through this modal participation vector, right? This is the vector that relates your single degree of freedom system or establish the relationship between your single degree of freedom system to the multi-degree of freedom system for which you actually want to find out the response. Okay, so you already know the expression for this, right? This is what? Phi n for seismic excitation. This S here would becomes mass times the influence vector. Okay, divided by Mn, which is basically this. And again, utilize your calculator to do matrix multiplication as well. Okay. So now what I want you to do, give me the value of this factor because I need these so that once I have obtained my single degrees of freedom system, I have those factors so that I can relate the response of single degree of freedom system to multi-degree of freedom system. Now, many times it would be asked to you, or it would be required for you to find out the excitation vector. What is your excitation vector here? Do you remember? The excitation vector P effective is what? It is nothing but minus ML, okay, times UGT here. Okay, so what do you need to do? Find out the expansion of this vector. Okay, so that is the next step. Okay, that vector is what? What is your M times L? M times L would be simply 350, 250 and 175 times 10 to the power 3. Okay, so this you need to find out what is this vector. So let us get the expansion. What I need you to do, find out S1, S2 and S3 so that this can be written as, let us say this is S here as S1, S2, S3. Okay, how do we get S1, S2, S3? Simple. You have already found out gamma 1, gamma 2, gamma 3. Remember, Sn is nothing but factor gamma n times phi times this vector. What here? Let us say I write here 10 to the power 5, 10 to the power 5 and 10 to the power 5. I just want these elements. That's all. Okay, so this is what you would get as S1, S2, S3. And what it basically means that we had initially, and let me write it like this here. This was 1.75, this was 2.5, and this was 3.5. Okay, the total vector due to applied force. Now, because of this applied force, I had inertial force in each mode. Okay, that I can write. This is 2.49, 2.29, and 1.49. Okay, the second mode is basically minus 9.0, 0.80, and 1.28. And the third mode is basically 0.73, minus 0.58, and then 0.73. Okay, all of these are multiplied with 10 to the power 5. Okay, I'm just writing down the internal numericals. So this is your S1, this is your S2, and this is your S3. Now, if you want to follow the procedure of equivalent static force, what is the equivalent static force in each mode? Fn is basically nothing but Sn times A and T, right? So all you need to do, find out A and T from Q and T. Okay, once you get that, all you need to do, multiply this with A and T here, A and T here, and A and T, which would be, let us say A1, sorry, A1T, A1T, and A1T. This A2T here, and basically this is your equivalent static forces. And it becomes so easy to find out the base shear in the first mode as, or story shear, whatever you like, sum of all these forces. Okay, because you already know. Similarly in the second mode and the third mode, and same goes for the story shear. So all you need to do now is find out the A12, A22, and A3T. Okay, now remember, you know what is your D and T, right? Either for the ground motion or for any other thing. This was the equation of motion. Remember, what was the equation of motion? D and T plus 2 zeta omega n d and t velocity plus t and t, and that is equal to, for ground excitation it was UGT, but it had not been a ground excitation. Then let us say blast loading or some triangular pulse or like some other type of loading, then it would be basically representing that history. But as long as you can find out D and T, you can find out your Q and T as this times D and T. Okay, or this is basically equal to an by omega n square t. Okay, and A and T, you can again easily find out. If this is your D and T, A and T is nothing but whatever D and T you get from there, just multiply with the omega square n, sorry, times D and T. So just substitute like here, and you will get the displacement response, sorry, in this case the force response, displacement response, and all other responses as a function of the total response. Now displacement response you can directly get U as summation of all U and T. So phi and T, Q and T for each mode. Now Q and T for each mode is what? Q and T for each mode is whatever gamma n times D and T is. Okay. So you can substitute that and get the total response. Now for the ground motion, D and T is not that easy to find, because for ground motion, what do? We do response spectrum analysis. So now let me give you the response spectrum. Okay. Your response spectrum or a design spectrum is a very simple spectrum, which is this. Okay, so I'm drawing it here. This is the pseudo acceleration as unit of g. So everything is given in terms of g. This is 0.4. This is actually 1 here. Okay, this coordinate. And this is for 5% damping. Okay. This Tn here 0.125 and this is 0.6 and this is T here. Okay. So now what you need to do here in this case, okay, or yeah, let us just do that. For each mode, you have omega 1, omega 2, omega 3. You need to find out what is your T1, T2, T3. Once you find that out, okay, it will give you the maximum response. That is, it will give you Dn max. Okay, so it will give you Dn max, or in this case A1 max, because it is acceleration is given. A1 max can be calculated. Remember this, sorry, I forgot to give you this. This is basically 0.5 times T divided by T. Okay. So you find out what is your A1 max, A2, A3 max. Okay. 2 max using SRSS method. How would you get U max? If A1 max, A2 max, A3 max is known, you can find out D1 max as A1 max divided by omega 1 square. Similarly, D2 max as like this, or you can directly find out UN max. Remember, UNT is what? Phi n times QNT, which I can write it as Qn I can write it as gamma n times dnt. Okay. If I write dnt as ant by omega n square, I can write it like this. So this is in terms of time. Now, if you want to find out UN max, you don't even need to calculate actually D1 max. Just do this. Find out, you know gamma n, you know omega n square, you know phi n. Just find out an max for each mode. Once you know u1 max, u2 max, u3 max, use SRSS as u1 max square plus u2 max square plus u3 max square to get an approximation of the total maximum displacement. Here I'm telling you that all three modes have the same damping at 5%. Okay. If it is told otherwise, then you can do something else. But here I'm telling you that all modes have the same damping value of 5%. Okay. Remember, when you are finding this, all of these are actually vectors, right? So just keep that in mind. In fact, this is also a vector. This would give you three values here, here, and here. And when you take the SRSS, it would be for the first degree of freedom, first degree of freedom, first degree of freedom, then second degree of freedom, second degree of freedom, second degree of freedom, and so on. T1 here comes out to be 1.39 second, right? Now, if T1 is known, let us look at where the T1 is. T1 is somewhere around here, right? So A max or A1 max would be basically 0.5 times 1.39, correct? And times multiplied by G. Okay, if you want to write it in terms of units. So this would be 4.23 meter per second square. Now, if A1 max is known, I can find out D1 max is required. But what I'm going to do, I'm going to directly utilize this expression. Okay, what was my gamma 1? If you remember, my gamma 1, where is it? Let me see. Gamma 1 was wait, did I write my gamma 1 here? 4266 minus 0.5118. Gamma 3 is 0.0892. So it is 1.4266 gamma 1. So just utilize this expression 1.4266. Omega 1 square is whatever the value of this one, or you can write 2 pi by t or whatever 1.39. I have only in front of me this, so I'm just utilizing this. Then phi 1, again just utilize this, whatever we had got here, 0.3, 0.64 and 1.0. Okay, this is 4.52 here. So 0.3, okay, 0.64 and 1, and this is 4.52. Okay, this time A1 max, which is basically 4.23. Now it will give me the U1 1 max, U2 1 max, U3 1 max. Okay, which actually for this case I get that as, let me just write it down here. Okay, 88.4, 189.4 and 294.6. These are all in mm. Okay, just keep that in mind. Similarly, this is my U1 max. Similarly, U2 max I can find out. Okay, that would be U12 max, U22 max and U32 max. Okay, some values would be there. Now to find out, similarly U3 max also. To find out the peak response using SRSS, the quantities that you need to combine would be this square plus this square plus this square under root. So what I'm saying, my Umax would be under root, because remember I have got the maximum at each degree of freedom, and this is what the response that I'm going to combine the peak responses. It would be U11 max square plus U21 max square plus U31 max square, then U21 max square, then U22 max square, and then U32 max square. Similarly for third one. Okay, and this will give you at each degree of freedom U1 max, U2 max, U3 max. See, it looks complicated, but once you go through and the steps and you are aware of it, you can quickly do all these calculations.